In this presentation, we will showcase one of our projects that makes a quadruped robot terrain-aware so as to make it suitable for outdoor applications. We started out with out-of-the-box controller provided by Unitree A1 quadruped robot. Our observations show that these default controllers are unable to adapt to varying terrains and unperceived obstacles. In real-world deployment, obstacles will be of varying sizes. Our main concern is to work with those that obstruct the pre-programmed gate pattern. If the obstacle is bigger than the max reachable gate height, then these will have to be circumvented via global planning and completely avoiding the path. For the obstacles that can be solved via intelligent locomotion, challenge is partially due to the discontinuous impacts that are made due to locomotion on unsteady terrains. One small slip can lead to drastically different outcome than planned. To efficiently utilize these robots, they must be able to reason about the hybrid dynamics that arises due to uneven contacts. We have identified two main problems that limit the utilization of their full capability. Number 1, limited adaptability to varying terrains, and number 2, limited agility caused due to high computational requirements. So the challenges that we would like to address are, number 1, model the rise of hybrid dynamics caused by discontinuous events, number 2, lack of efficiency of the control algorithms that come out of the box, and number 3, they do not provide a framework that can leverage machine learning and artificial intelligence algorithms to integrate with their controls. Our solution to address these challenges is to model the dynamics that arise when they operate on uneven terrains and apply necessary control algorithms to negate the unwanted effects of these hybrid dynamics. First, we model the cojoint robot and terrain dynamics in our hierarchical bilevel hybrid dynamics modeling section. Here we introduce a novel IMU exoskeleton-based proprioception that helps in modeling the instantaneous terrain effects. This modeling is injected with the intended center of mass trajectory and the 12 actuator states of the robot. The hierarchical 3-layer control module consists of a top layer that calculated the necessary ground reaction forces, middle layer that compares the calculated ground reaction forces to the ones actually seen on the robot, and bottom layer that utilizes a fast proportional derivative controller that gives necessary torque output to the actuators. Please refer to our paper given in the description box for more details on derivation and analysis. Classification of the terrain was done via k-means classification, where we provide a carefully curated samples of each terrain type via IMU proprioception technique. Here we show 3 terrain types that were the subject of classification: grass, concrete and loose gravel that consisted of small rocks. The IMU accelerometer values were fed as the input, and one class was selected out of the 3 via softmax function on the output layer. Next, for each classification of the terrain, we train the robot model in Isaac Sim environment and provide necessary terrain properties as domain randomization parameters and reward only the actions that lead to a stable gate that follow the commanded velocities. We save these models as F1, F2, F3, and so on up to Fn. And during real-world deployments we switch between these saved models based on the confidence level of the proprioception model for the terrain. The switching methodology may induce chatter when the terrain is highly mixed. An upgrade to the switching framework is our adaptive robust control framework. Here we calculate the torque requirements parallelly from all the saved dynamic models and blend it together so that the transition from one model to other is a weighted sum of all the models with proportional weighting scheme. Finally, our overall control architecture is shown in this slide, where we demonstrate, when a user gives the velocity commands, we convert the commanded center of mass trajectories into necessary ground reaction forces via model predictive control paradigm. Then these values are provided to the proprioception module, where it compares the current values to the ones received. This continues in a cyclic fashion on the real robot during deployment. Here we show a simulation of the implemented framework on a ROS Gazebo platform using Quad SDK library. To conclude, we show the results from our outdoor experiments and validate the implemented methodology. Finally, for the scenarios when the robot encounters some extreme cases, we have included a reset control module that autonomously makes the robot stand and continue its operations. With this, we hope that in future, quadruped robots can help us in search and rescue operations, and survey missions, where human presence is undesirable, including nuclear power plants and Mars colonization projects. We thank you for your time and attention.